but there's a few things we have to talk about first. Okay, so number one, so I showed you composition in the previous lecture. You saw that if you use composition, what ends up happening is you end up having to pay the price of making copies of objects. In many cases, you don't want to pay that price. And so you would reconsider whether or not you'd have to use composition, or if you could use some other technique to implement the class that you're trying to implement. There are conditions, though, where you have to implement, you have to use composition. And so that's the discussion of today's lecture. So remember earlier in the course, we talked about class invariance. So a class invariant is something that a class promises will always be true about the state of its objects. Right? So for example, our counter class says that the counter value will always be between 0 and some positive value, right? It's never negative. So if you decide to implement a class, one or more of its fields are of reference type, and that type is mutable, you have to use composition if your class has an invariant that involves the state of that field. Okay, so here's an example of such a class. So this is the period class. So it represents a period of time. So you might want to use this class if you're implementing, say, a calendaring example. A calendar application or something like that that lets you schedule your time. So every period of time has a start time and an end time. And it only makes sense if the start time comes before the end time. Right? So I think our class invariant is that the end time is always after the start time. So you can't have a period of 0 length. All right, so if we're going to implement this class, we need some way to keep track of 2 points of time. And so I'm going to use the date class to do that. So when in choosing to use the date class, it's a reference type. So now I have to consider, am I using aggregation, association, or composition? Right? Date is mutable, and there is the class invariant involves the date fields, right? The end time is always after the start time. So we have to use composition here. I should say before we finish this example, or before I explain the example, it's probably incorrect to use the date class here to represent the start and end time. Right? You can avoid all these problems if you use a different type. But if you choose to go ahead with this, we have to use composition. So we're going to use one date object to represent the start time. We're going to use a second date object to represent the end time. Here we have to use composition, right? I can't expose the start time object, and I can't expose the end time object to people outside the class, right? If I do that, they can change the start and end time so that the class invariant is no longer true, right? So in other words, they can move the end time before the start time. So that's a problem. When you draw a composition relationship as a UML class diagram, it looks exactly the same as aggregation, except the diamond is solid. Right? And that's the only difference in the UML class diagram. Right? So open diamond means aggregation, solid diamond means composition, no diamond means association. So here, this picture is saying a period is a composition of 2 date objects. Okay, so the date class is funny. In fact, it's so funny that the recommendation is that you don't use it anymore. We're going to use it anyway. Right. Date has no copy constructor, and we know that in composition, you've got to copy. There is a tendency to need to copy the date objects in this case. Right. So to copy a date object, the way you do it. So if I want to copy D, right, you can't just write new date D. Unfortunately, you have to write new date D dot get time, and get time returns a long value, I think, that represents the current time. And I forget exactly how it keeps track of time, but I believe it's the number of seconds since January 1, 1970. Anyway, that's how you copy a date. Okay, so when you start to implement the class, there's nothing difficult here, right? There's my period class. I have a start time and an end time. They're represented by 2 date objects. Right? Yep, sorry. Okay, so we want a constructor. And the constructor that we want the constructor that we probably want will allow the caller to specify the start and end time of the period. So there's 2 parameters to our constructor, right? The start time and the end time. If you implement the class as an aggregation, right, you'll run into problems right away. So here we actually do the correct thing, right? We validate the start time and the end time. Right? We compare the start time to the end time using the compare-to method. Right? So if you go and look at the date class, you'll see that date implements comparable, which means you can compare two dates chronologically, right, by time. So if the start time is greater than the end time, right, that means the start time comes after the end time, that's a problem. Right? So we're going to throw, I guess it should be greater than or equal to. But anyway, we're going to throw an exception to indicate that the start time comes after the end time. Now, when you write this start equals start and this end equals end, right, you have to remember what is it exactly that you are writing, right? You're saying that the object this dot start or the field this dot start refers to the exact same object as start, right? And the field this dot end refers to the exact same object as end, right? Whoever called this constructor, right, has a reference to the internal start and end field belonging to the date object. That means they can use that reference to change the start and end time. So here's the caller, right? They make a start time, they make an end time, and then they make a period object using their start and end time. Right? So the caller can now break the invariant of the period class, right? They can now set the start time or the end time, the start time to come after the end time, right? Or the end time to come before the start time. So the date class has a method called set time that takes in a long value that encodes the time. So end set time and get time. If you just look at that, it sort of that says that that doesn't change the end time at all. Right? And get time returns the current time for the end. Returns the time that the end object represents. Right, and so setting the time to end get time doesn't change the end time at all. Right, so that does not break the class invariant. And get time plus 10,000 adds 10,000 milliseconds, so 10 seconds to the end time. So that moves the end time further into the future. That doesn't break the invariant either. And get time minus 1 is 1 millisecond, I think, before the end time. Right, so the start time is still before the end time, so that doesn't break the invariant either. But the last line there will break the class invariant. Right, if you set the end time to the start time, you now have a period of length 0, which we're not allowing. So without touching the period object, right? So this is the point, right? Without using P, right, you can break the class invariant. You never have to ask the period. So you can change the start or end time of the period object without ever asking the period object itself. And that indicates that you have a privacy leak, which indicates your composition is broken, which means there's no way that for the class to promise that its class invariance will always be true. Right, so you've now got a busted period class. Right, how do you fix it? You fix it in the exact same way you fix any composition, right? You make sure to copy the start time and the end time. Right, so the very first thing that we do is copy the start time and the end time. Right, validate the copy. So validate start time and end, start copy and end copy. Right, if you pass the validation, now you can go ahead and set your internal fields to refer to the copied objects that you just made. Right, and it's the same pattern every time. Right, make the defensive copies, check the defensive copies if you have to, then assign your fields to the defensive copies, rather than assigning them to the objects that were passed in by the caller. Same is true of the copy constructor. Right, so here's our copy constructor, which is incorrect. This start equals other start means this start, the object that this start refers to, is the exact same object that other start refers to. So you now have two period objects that are sharing the same start and end time objects. Right? If one period object changes its start time, the other period object now has a different start time, right? Or now has a modified start time. How do you fix it? You have to copy other start and other end. It's the exact same thing all the time, right? You're making these defensive copies. Here are the accessor methods, right? So if you have a period class that represents a start time and an end time, users of the class probably want to know, given a period object, what is its start time? What is its end time? Right? If you return this start, or if you return this end, right? Those are both privacy leaks. You handed somebody a reference to your internal date objects. They can now change the state of those date objects, right? How do you fix it? Well, I guess it's the same story all over again, right? Make sure you make a copy of the start time, right, and return a reference to the copy. And finally, you have a mutator method. So the mutator method lets you change either the start time or the end time. Here, we validate the new start time, right? So if the new start time is less than the current end time, everything's fine, right? But now when you write this start equals new start, you have a problem, right? You're saying this dot start refers to the exact same object as new start, right? Whoever has that reference to new start can now change the start time of the period. Right? How do you fix it? Copy new start. Right? So make a copy of new start, and then validate the copy. Okay, so this one slide summarizes basically everything that we talked about in the last 2 days, right? So a privacy leak occurs when a class exposes a reference to a non-public field, right? That is not primitive or immutable, right? So if you have a reference type field, right, and it's mutable, and you expose a reference to that field, that's a privacy leak if you're implementing a composition. Right? If you're implementing aggregation or association, it doesn't matter, right? The whole point of aggregation and association is that you're willing to share the internal objects. So for a class X that has a field of type Y, right, all of the examples here are privacy leaks. Right? There's a constructor that takes in a Y object. Right? There's a method that returns the Y object. Right? There's the copy constructor, and there's the mutator method, right, that changes the Y object. So you can't do any of those in a composition, right? You have to remember to make the defensive copy. Okay, so what happens if you forget to make the defensive copy, right? So in other words, what happens if you have a privacy leak? Right. So if you have a privacy leak, that allows a different object to control the state of the object that leaked the field. Right. So if a period object leaks one of its date fields, and some other object that gets a reference to one of those fields can then change the state of the period object. So what happens if the state of the object changes? Well, it can become inconsistent. Right. You might break your class invariance. Right. So for example, if a credit card exposes a reference to its expiry date, right, then the client could set the expiry date to become before the issue date. It becomes impossible to guarantee class invariance. Right? So if period leaks either one of its date fields, then anybody that gets a reference to one of those date fields can then break the invariant on the period class. Right? They can move the start time after the end time. So your composition is now broken. Right? The object no longer owns its own field. So when an object that represents a composition dies, so in other words, when you're done with that object, the parts that make up the object may not die with it, right? If someone has a reference to one of the fields, the way it works in Java is that those objects cannot go away until whoever has references to those fields no longer uses those references for anything. All right, so if you are creating a class and one or more of its fields are mutable reference types, and if you want your type to be immutable, right? So you want to make an immutable class of some kind, right? Then one of the things you have to do is you have to use composition. Okay. So string is an example of an immutable type. So if you look at the string class, right, and you look at all of its methods, right, you will not find a method that changes the state of the string. Okay. So that's requirement number one. Okay. If you look at the string class in greater detail, right, so if you actually look into the source code and you go and find its fields, you might find that its fields are all marked as being final. Right. So remember what a final variable is. Final variable, final field, it's all the same thing. Right. Final variable is a variable that can only be assigned to once. Right. And so you want to make your fields be final in an immutable object to prevent errors that you might make when you implement the class. Right, so to prevent you from accidentally reassigning one of your fields to a different object. You have to make everything private. If you don't make everything private, then a different class, another class is able to access those fields. Right? If you make them package private, any class inside the same package can access the field by name. Right? If you make them public, then any class anywhere can access those fields and modify them by name. Step 5 is basically use composition. Right? Step 2, we don't know about yet. That's going to be the subject of a future lecture. Right, so we're going to talk, we'll come back to this point when we talk about inheritance. Okay, so we're not quite done with composition and aggregation yet. So far, we've only talked about compositions where the fields are single objects. Right? But many classes that you might implement are actually collections of objects. Right? So for example, you might implement a class that has an array as one of its fields. And so in Java, an array is a reference type. Furthermore, it's a mutable reference type, right? You can go in and change the elements of the array. So if you're implementing a class that has an array, you need to consider whether or not you should be using aggregation or composition. So I'm going to deal with the simple case first. You have an array of elements, but the array, the element types are primitive. Right? So you have an array of int, or you have an array of double, or something like that. Right? If you have an array of reference type, that becomes more complicated, as you'll shortly see. Oops, sorry. All right, so simple class that uses an array to hold some primitive values. So we're going to implement a little combination lock. So a combination lock is one of these old locks that you have. They usually have a dial or something on it, right? And you turn the dial or dials to different numbers, right? And that unlocks the lock. So this class represents a very old school combination lock. It has 3 or more dials, right? And each one of the dials has a number between 0 or 9. And the lock is either locked or unlocked, right? So it has a combination, right? And it has a state, right? Locked or unlocked. So to implement this class, we need some way to store the digits, right? The combination itself. So here I'm going to use an array of int, right? Furthermore, you need something to represent the state of the lock, right? Is it locked or unlocked? So there's only 2 states, so it makes sense to use a Boolean value here, right? True for locked, false for unlocked. Okay, not hard to implement this class. So here we have combination lock. I don't know why we're implementing comparable. I guess we can compare 2 combinations by looking at the values of their digits. It's here, I guess. Right, there's our combination. It's just an array of ints. And there is our is locked field, right? True for locked, false for unlocked. Okay, so remember that variable there, right? Combination is a reference to an array of int, right? There's no array yet. So before you, so in the constructor, you have to make the array of int. So there's our no argument constructor. Our no argument constructor makes a 3-digit lock whose combination is 999. So make the array for the combination, right? Store it in this combination. Fill in the values of the combination. So set the 3 values to 999, right? And set the lock, make it be a locked lock. All right, so what if you decide to have a constructor where somebody can pass in the combination, right? So the way this class works, it does have an invariant. It has a few invariants. So one of its invariants is that the length of the combination is at least 3 digits, right? Each one of the digits is between 0 and 9. Right? So in your constructor that accepts a combination from a caller, right, you have to validate the incoming array. And so I don't validate whether or not the values are between 0 and 9. That doesn't fit on the slide, right? So it would be here where you would do that. So instead, I only validate the length of the combination. Right. So this is a composition, right? What do you do in a composition if you're passed in an object that you want to use as one of your fields? Right? You have to copy the object. So here we have to copy the array. Right? And it would not be surprising if most of you forgot how to copy array by this point in time, right? We talked about arrays several weeks ago. But remember, arrays, the class arrays has a method called copy of that will make a copy of an array for you. Right. So array is copy of combination, comma, combination length makes a copy of the array combination. We can now validate the copy. Right? So if the length of the copy is less than 3, right, that's not a valid combination. You should also make sure that each digit in the combination or each value in the combination is between 0 and 9. Once you've validated the copy, you can go ahead and set this combination to refer to the copy. Okay, what about the copy constructor? So we have a reference field, right? And we want to make sure every combination lock has its own combination. So you have to make a copy of the other combination blocks array. Right? And so here we're doing what's called constructor chaining. And I don't remember if I showed you how to do this in an earlier lecture or not. I can't remember anymore. I have a feeling that we might have skipped this. So let me explain what this does right here. So that one line right there is calling another combination lock constructor. Right. So on the first line of the constructor, right, you are allowed to call another constructor in the class. So I want to call this constructor because that constructor there copies the combination for me and then does everything correctly, right? So I'd like to reuse that code. So the way that you call another constructor in the same class is you use the keyword this. Okay. So Java recycles the keyword this to allow you, in a constructor, it allows you to call another constructor, but only on the first line of the constructor. Okay. So writing this bracket other combination calls the previous constructor, right? Passing in the other locks combination. Right. This constructor now runs, right? So it makes a copy of the other locks combination. Right? It validates it, and then it assigns our fields. We have to remember that in the copy constructor, we're also copying the state of the other lock. Right? So here we're going to set this is locked to whatever value other is locked is. Here we're not making a copy of other is locked. Right? It doesn't make sense to make a copy of this. It's a primitive value. Right? And so primitive values, you never worry about copying them. Right? You simply do the assignment and everything works the way you want it to. Right? So there's an example of what's called a constructor chain. I don't think you'll be asked about it this year in the exam. Because I have a feeling we didn't talk about this. Anyway. All right, so one of the mistakes that, well, no mistake, one of the things that students will do when they see composition for the first time is that they will remember, I've got to make these defensive copies. So they will copy everything all the time, right? And that just makes an unnecessary number of copies. So not every method needs to make a defensive copy. So if you want to unlock the lock, somebody has to pass in a combination, and you're going to check whether or not that combination matches the combination of the lock. Right? You don't have to make a copy of the array that they passed in this case. Right? The combination that they're passing in, or the array that they're passing in, right, is never used to modify your lock's combination. Right? So there's no point in making a copy of it. Right? There's no possibility of a privacy leak here. Right? So unlock, right, takes in a combination, right, and you're going to check, right, does that combination match the combination of this lock? Right? In other words, are the two arrays equal? Right? So arrays has an equals method that will test if two arrays are equal. So you can directly test this combination against the array that was passed in. Right? You don't have to copy that array because you're never changing that field there. Right? So here, there's no need to make a defensive copy. Right? If the two combinations match, you're just going to unlock the lock. All right, so there is a composition when you're using an array of primitive elements. Okay. And as you can guess, right, the next set of slides talks about composition when you have a field that represents some collection of stuff, right, where the stuff is not of primitive type. Right. So often you'll have a class that has a collection as a field, right? And so here are some of the examples we talked about before, right? That's a new one, right? So a receipt has a collection of items. Contact list would have a collection of contacts, right? This is from a different version of this course, so ignore that, right? The one I'm going to use today is something called a polygonal model, right? That has a collection of triangles, usually triangles, right? I'm just skipping ahead a couple slides here. This is an example of a polygonal model, right? So if you ever played a 3D game, then almost certainly, right, the objects in the game are made up of a bunch of triangles, right? They might be made up of a bunch of quadrilaterals, but it's probably triangles. The reason they're made up of triangles is because a triangle is always flat, and that is important for how you color in the triangle. Okay, so here that looks sort of. This is a very old picture, if you look at the ball, it looks round, right? If you look at the apple, it looks round. If you look at the Zerg, the Protoss, he looks round. He looks pretty smooth too, right? Even the ground looks pretty smooth, right? And so if you look closely at the perimeter of the objects, right, you can see that they are linear, right? So they're made of a bunch of straight lines, right? And so there you can see the artifact, or the fact that they are everything in this picture is in fact made up of triangles. If you take CISC 454, the computer graphics course, you'll learn all about this sort of stuff. Okay, so let me back up here. Right, so that's going to be the example that we're using in this lecture. Right. So before we move forward, I have to tell you what exactly does a collection hold. Okay. So if you have an array or a list or a set or a map or a list, any one of the above, right, or any other type that represents a collection of stuff, right? The collection does not hold the objects, right? So an array does not hold objects, right? An array of string does not hold string objects, right? A list of dates does not hold date objects, right? And similarly, a set of points does not actually hold the date point objects. It holds references to the objects, right? Everything in Java, every variable that you can access is a reference variable. So here's an example here where I make a list of dates. I have 3 dates, D1, D2, D3, right? Notice new, new, new. So there really are 3 date objects. There's a new array list, so there really is one list object. Right? And I'm going to add these 3 dates to the list. Right? So dates add D1, D2, and D3. Right? So what does this look like in memory? So here I've got a very simple sketch of a memory diagram here. Right? So here is there is our list object. Right? There is the client's dates variable. Right? So dates is the list at address 200. Right? So right there. Okay. D1, I don't have room on the slide. Right? But D1 is a date object at address 500. Right? And D2 and D3 are date objects living at addresses 600 and 700. Okay. If you were to able to look inside the array list object, right, you would find a bunch of fields. Right? One of those fields is going to be an array, right? And inside that array, you would see that it is holding references to the date objects, right? So the object, the date at address 500, the one at 600, and the one at 700. Right? So the list itself does not hold the dates, right? They are somewhere else in memory. It's holding references to the dates. So if you remember that the list itself is not holding copies of the dates, it's holding references to existing dates, you should be able to decipher out what the following prints. Right, so PTS is my list of points. Right? P is a new point or refers to a new point. If you add P to the list, right, and then change the X coordinate of P, right, what do you get? Right, so when I print out P, well, you're going to get 10, 0, right? So it's got to be one of C or D. Okay. And so now if you ask the list to get the point at index 0, there's only one point reference in the list, right? It's P. Right. So if you ask the list, right, to print out, or sorry, if you print out the point that's in the list, right, it's also 10, 0. So adding the point to the list here, right, does not put in a copy of the point 0, 0. Right? It puts in a reference to the point 0, 0. Okay. P dot x10 changes whatever point P is referring to up here, so that its coordinates are now 10, 0. Right? The list has a reference to the exact same point. So the list is not making copies of stuff, right? It's just taking references to the objects that you pass in. And so points get 0, while it's just the point P. So this also prints out 10, 0. Oh, sorry. Why is this here? Okay. All right, so if you're going to draw a UML class diagram and the class involves a collection of some kind, the UML class diagram does not typically show the collection itself. Right? So here's a made-up class called student. Right? Every student has some collection of GPAs, right? And they have some collection of courses. It doesn't say what kind of collection it is, right? And they have a string that represents their student number. Right. So this is, it looks like this is a student is showing it's an aggregation of stuff. Right. So this picture says a student is an aggregation of one string that represents its ID. Right. And instead of having student has some relationship to a collection, right, this simply says that a student is an aggregation of 0 or more GPAs. Right. So here it's the elements that are being shown, right? But the collection itself is typically not shown. Right. You can show the collection if you need to for some reason, right? But typically in these UML class diagrams, you show the elements rather than the collection itself. Right. So student is a collection of 0 or more courses. Right. It's not student is a aggregation of a list of courses. Right. So for our polygonal model class, our polygonal model, it looks like it's going to be an aggregation of 0 or more triangles, right? Where every triangle is an aggregation of 3 points. Right. So every triangle is made up of 3 points. So this makes sense here. There's our example again. Okay, so to implement this thing, we're only going to implement a couple of methods, right? So first of all, we're going to add a field where we can store our triangles. Right. So back up here, right? So we need something that can store 0 or more triangles. You can use an array here, right? I'm going to use a list. Right. So here we have a list of triangles called tri. Our constructor simply makes a brand new list, right? And it's empty. So we have a model that has 0 triangles in it. Again, remember here, tri is a reference variable, right? That can refer to a list, but there's no list yet, right? Up here, you did not write equals new array list, although you could, right? So the constructor has to make sure to initialize or to make a new array list object and assign it to this.tri. Clear simply removes all the triangles from the polygonal model, right? So how do you do that? Well, every list has a clear method that removes the elements from the list. So this try.clear works just fine, right? And size returns the number of triangles in the model. So we're just going to return the number of triangles in its list. So that's this.try.size. And those are the only methods that we need for this example. Okay, so now you've decided that you have a class that has a collection as one of its fields, right? And now you need to decide on the ownership issues. Okay. So there's two things now that come into play. Right? There is the collection itself, right? So there's the list itself for the polygonal model class. Similarly, there are the triangles in the list. Right? And if you think about it just a little bit more, there's also the points in the individual triangles. And now you have to decide, what exactly is it that the polygonal model owns? Right? Does it want to own its collection, or is it willing to share its collection? Right. So do we want to own our own list, or are we willing to share the list with someone else? Right. If we own the list, right, we now have to decide, well, am I going to own the stuff in the list? Right. So if we own the list, does it also own the triangles that are in the list? And if we decide that yes, we own the triangles, we now have to decide, do we want to own the points that make up the triangles? Okay, so the simplest case is your class X decides that it's willing to share its collection with anybody else. This says with other X's, but never mind, with anybody else. So this is, it's written this way because I'm only talking about the copy constructor here. Okay. So if your polygonal model is willing to share its list, then you just implement the straight aggregation, right? You don't have to worry about anything. So here's our copy constructor. Right? We're gonna try to copy another polygonal model. Right? We're willing to share our list with anybody else. Right? So you can simply write this trie equals other trie, and away you go. Right? You don't have to make a new array list for this trie. Right? Whatever list belongs to other trie, that'll do just fine. If you decide to add an accessor method, right, and you're willing to share your list, you can just return this dot trie. Right? So this is just straight up aggregation. What does it look like in memory? So here we have an existing polygonal model P1. We're going to make a copy of it by using the copy constructor. So we have a second polygonal model P2. Right? You know for sure there are two polygonal models. Right? There's the existing one P1, and then you call new and a polygonal model constructor. So you know there's a second one for sure. So there are our two polygonal models, P1, P2. Right? What's inside the polygonal model? There's a reference to a list. Right? In our current example, there's only one list, right? It's the one that P1 made. So there's the list, right? And it lives at address 700. Right? Model 1 and model 2 have a reference to the same list. Right? What's inside the list? There's a bunch of references to triangles. Right? So this list has a reference to a triangle here and a second triangle here, and so on and so on and so on. Right? So two polygonal models. Right? There's two objects. Sorry. Two polygonal model objects, one list. Right? Two triangles. Okay. So we're going to make a copy of P1 using our copy constructor, right? And then using P2, right? So using the second polygonal model, right, we're going to clear its list of triangles. Right? So what's the size of P2? Going to be 0, right? You cleared the list belonging to P2. What's the size of P1? Well, P2 and P1 are sharing the same list, so it's also 0. Right? So you get 0 and 0 in this case. Right? Is this broken? No, it's not broken, right? This is just a consequence of using aggregation, right? You're willing to, the models are willing to share their lists, right? If one object modifies the list, all other objects that are sharing the list also see the modified list, right? So here, clearing model P2 also clears model P1, right? Because they're sharing the same list. Okay. So suppose you decide, well, look, this isn't what I want to happen, right? If I have P2 and I clear its list, I only want P2 to have 0 triangles in it, right? I want P1 to still have its triangles. You say, oh, fine, right? This means that I cannot share the collection, right? So in other words, I have to have my own list. Right? If you have your own list, you have to make a separate copy of every object needs to make its own list object. Right? But now you have to decide, do you also want to own the elements in the list? So here the answer is going to be no. Right? We're going to make a copy of the existing list, but we're not going to copy the stuff that is inside the list. So this is what's called a shallow copy of the list. Right? You have a new list, so it's a copy. Right? But you did not copy all the objects that the list is referring to. Right? So that's why it's called a shallow copy. Right? You have two lists, but their elements all refer to the same objects. So the picture doesn't change, right? It's still an aggregation of a bunch of triangles, right? Each polygonal model is willing to share its triangles. It's not willing to share its list. Right? So the model doesn't change at all, right? This is still an aggregation of triangles. Okay, so the hard way to make a shallow copy of a list is to make a new list object and then write a loop, right? And copy and add the elements from the one list to the other list. Right, so here I'm showing you how to make a shallow copy of a list of dates. So there's an existing list called dates. Right, scopy is my shallow copy. Right, I need a new list. It's a copy. Right, so there's my new list, and then I write a little loop. Right, the easiest way to do this is with a for each loop. So for every date d in dates, add d to the copy. Right, and that's what the add method does for lists. Right, it adds the reference to the list. It does not add a copy of the object to the list. You never have to do this. Okay. List and set, they all have a copy constructor that will do exactly that for you. Right. So to make a shallow copy of an array list, call the array list constructor, pass in the object that you pass in the list or the set that you like to copy. Okay, so now I'd like to modify the polygonal model class so that it owns its list, but it does not own its triangles. Okay, so here you make a shallow copy of the list. Okay, so instead of writing this trie equals other trie, right, you now write this trie equals new array list other trie. Right, so make a new list, but don't copy the stuff that's inside the other list. And now your memory diagram changes slightly. So still two polygonal models, right? But now each polygonal model has a reference to its own list. Right? So model 1, list 1, right? Model 2, list 2. Right? When you look inside the lists, right, you will see that the lists are identical, right? So the first list has references to triangles at addresses 1000 and 1100, right? And the second list has references to triangles at address 1000 and 1100. If you were to change this triangle, right, both lists contain a reference to the changed triangle. Right, but they have but each model has its own list. So now, if you make a copy P2 of P1 and clear P2, right, P2 size is definitely 0, but P1 size is not 0 anymore, right? It doesn't change as well. P1 has its own list, right? So now you get 0 and 100. Right, so now you can clear the list belonging to a polygonal object model without worrying about any other polygonal model object. Okay. So here I have a P2 and P1. They're copies of each other. Right. Triangle T1 is the first triangle belonging to P1. Right. Triangle T2 is the first triangle belonging to P2. Is T1 the same object as T2? Right. Remember, that's what equals equals does for two references for two reference types. Right. Are they the same object? The answer is yes, they are. Right. You go back to the model. Go back to the picture. Right. That's the first triangle in list 1. That's the first triangle in list 2. Right. They're both the triangle at address 1000. Right. So they represent the same object. So equals equals returns true in this case. Okay. Last step. Suppose that you want each polygonal model to own its own triangles. Right. So now each model needs to make each model needs its own list. Right. And the stuff inside each list each model must make its own list. When it makes its own list, it has to make sure that the references that are in the list are not shared with anybody else. Right. So here in our copy constructor, we have to copy the list and we have to copy the objects that are in the list. Right. So here's where the picture changes now. Right. So now in this now we're saying polygonal model is a composition of triangles. Right. So in other words, every polygonal model wants to own its own triangles. Right. So here we have to make what's called a deep copy of the list. Right. We have to copy the list and the objects that are inside the list. So to copy a list of dates called dates, right, step one, you have to make a new list, right? And now you have to iterate over the list you want to copy, and you have to copy the objects out of the other list. So when you add the dates D from the list dates, right, you have to make a copy of each date object. Right? So call the copy constructor for date, right? Copying the time for each date D, right? And add the copy to the list. These are all defensive copies, by the way, right? Everything that you're making a copy of, these are all defensive copies. So for the copy constructor of polygonal model now, right, we have to make our own list of triangles. We now have to iterate over the other list of triangles, right? So for each triangle T in other get triangles, right, we have to make a copy of each one of those triangles, right? So copy each triangle using the copy constructor, add the copy to our new list. And now, when you look at the memory diagram, it looks like the following. So there are two polygonal models. Right? Each one has its own list, so that's good. Right? Now, when you look inside the lists, right, the references in the list are different. Right? We made brand new copies. Right? So this was the original list, right? So it has triangles at address 1000 and 1100. In our second list, right, we made copies of that triangle, right? And so that's the triangle at address 2000, and we made a copy of that triangle. So that's the triangle at address 2100, right? And so now you have 4 triangle objects in memory. So 2 models, 2 lists, 4 triangles. Okay. So back to the original question, right? If I make a copy of P1 and clear P2, what happens to the size of P2 and P1? P2 size is 0, right? P1 size is still 100, right? The lists are independent. What happens when I get the first triangle out of the first list and the first triangle out of the second list, right? Are they the same triangle, right? The answer is no. We made a copy of the first triangle when we copied the list, right? So these are no longer the same triangle objects. Are they equal? Yes, they're equal. We made a copy of the triangle, so they're certainly equal, right? But they are not the same object. So this is false true. Okay, you can keep on going. Right. Here, a polygonal model is a composition of triangles, right? But you might decide, hey, the model is actually a composition of points. So now you have to, when you copy each triangle, you also have to copy the individual points belonging to the triangle. Right? And you can't do that with the triangle copy constructor, right? The copy constructor doesn't do that. Well, sorry, our copy constructor for triangle doesn't do that. So you'd have to manually copy out the points yourself somehow. Right? If point 3 was an aggregation or a composition of something else, you would have to decide then, right? Do you also want to own whatever objects point 3 is made out of? And so on and so on and so on and so on. Right? So you can keep on going. This chain of copying might have to keep on going and going and going. All right. So to summarize, in a composition, right, you are making a bunch of defensive copies of your internal fields. Right. The reason you're making these copies is because in a composition, the object owns its individual parts. Right. It owns the objects it's made out of. You cannot hand out a reference to one of the individual parts, right, in a composition, in a situation where you have to use a composition, right? If you do, the composition becomes busted. Right? Typically, what happens is that the reason you're using a composition is because you have some sort of class invariant, right? If your composition is broken, your class invariants no longer are guaranteed to be true, right? And that basically breaks the correctness of your class. When you have a composition involving a collection, right, you have to decide whether or not you also want to own the stuff inside the collection. If you do, right, you have to copy the elements from the collection, and you also have to copy the collection itself. All right, so I guess that wraps up our discussion of composition.